I want to ask you a simple question. How do you write the best dot product for your problem? And I'm going to show you some API ideas that some of you know I've been iterating on in a lot of different forms over time. And I'll show one example of one particular implementation and briefly sketch out some of the other approaches, and then I can tell you the rest later. So this is a part of a project I've been slowly working on for quite a while, involving like how do we do nice array computation for Haskell. So what's a dot product? Is it just I sum over some index space and explicitly do product over every entry and then add them together? Is it that I write repo code that looks like that and hope it fuses? What's it? I mean, you know, why do dot products matter? Well, why is it writing an efficient dot product matter that might not look like that other stuff? Well, I don't know. There's this really faddish thing called data science and machine learning where like they track all your behavior online and compare it with a billion other people. But most of the entries in the vector are 0, so you don't really want to do a lot of work just adding zeros together. So what are some tools you might use to engineer that? So here's a minified version of a type class I wrote a while ago, where basically the idea is you have an array data type. This is a little specialized to just be one-dimensional. You have an associated address representation for that data type. You also have the idea that you can always say what are the largest and smallest addresses I can materialize for that array. I can always say for a given address, I can always say give me the next, shift me up and down in the address space. I can always successfully turn an address back into an array index. And if we click through, I can also read from a location, and I can also say give me the next valid address if it exists. There's a bunch of other stuff, but this is all I really need to demonstrate writing some stuff. So actually for writing a dot product, there's actually 3 different algorithms you'd actually want to use. And do a few tricks where just using that interface, you can detect which of these 3 cases you're actually in. Again, I'll only be showing part of that. But basically, it's 2 dense vectors, a dense and a sparse vector, or 2 sparse vectors. Okay, so let's look. So this is a lot of code to fit in one page. It's just the vanilla dense dot product. I'm saying what's the largest and smallest address location that exists in a dense array. This code actually exploits certain invariants I have about what addressing a one-dimensional dense vector will look like. I don't go into how I use some of the operations I showed you for 5 seconds earlier. It does that. But this is just like, you know, doing the normal dot product. But you can actually go a lot further with those operations I mentioned earlier. I can use that, the thing I call basic cardinality to say, given an addressable range of a vector, how many things are in that range? And then I can compare that with the cardinality of the min and max of the int index space that it uses and say, do they agree? And that's how I can actually, oblivious to what instance of this class I'm working with, detect if a vector is dense. And that lets me actually do the selection for different vector formats. I don't know, I can talk about more of this later for anyone who's interested, and thank you.